Chapter 8, Energy of a System. So in the previous two chapters, we introduced Newton's three laws of motion, especially Newton's second law, and we saw how we can apply Newton's second law to find solutions to particle dynamics. Essentially, the procedure goes like this. You have a system, which can be a particle or a system of particles of the same acceleration. You want to analyze the forces acting on them, the so-called external forces. Given all these forces, we can apply F equals ma to find the acceleration. And once you know the acceleration, you can also find other things like velocity, position, et cetera, using things like integration. So that's the basic thing about particle dynamics. Everything is really in Newton's three laws, especially Newton's second law. Now, in principle, everything that you want to know about particle dynamics, or more general, classical mechanics, can be summarized in Newton's laws, especially Newton's second law. So in this sense, everything from this point on in classical mechanics will be just an application of Newton's laws. There's nothing fundamentally new. Okay, so in this sense, if I ask a question, is that all there is to it when it comes to classical mechanics, other than Newton's three laws, especially Newton's second law? Well, in principle, you can answer, yes, that's all there is to it, because everything else, if there's anything, will have to be derived from Newton's laws, right? Now, this doesn't mean that F equals ma in its original form always provides you with a simple and efficient answer. We've looked at problems where F equals ma can be used to solve problems efficiently, because that's a case where all the forces can be found, and they're most often than not constant forces. They do not change over time. You just have to locate all these, identify all these forces, and do a force analysis, draw a free body diagram, and you can find the acceleration accordingly, and you can go from there, right? And this does not always solve all the problems, and you will see from this chapter on, there will be problems that cannot be solved easily from the original form of Newton's second law. Well, the thing about F equals ma is that it is an instantaneous equation, okay? Instantaneous equation, what does that mean? It tells what happens at one moment, all right? So let me write that down, instantaneous. Okay, given F at one moment, I can tell you what happened. You can find A at the same moment. So what is A? A is the acceleration, which is the rate of change of velocity, right? That's what A is. So it basically tells you, once I know F, I can find how fast the velocity changes. That is how fast it changes. Doesn't mean it is the amount of change. Okay, so it basically tells you the rate. It doesn't tell you the amount of change that has already occurred. So if you want to know the effect of a force, it's not just how much force there is. You have to tell me something else. In addition to the force, you have to tell me something else. You have to give this force an opportunity to act on the system to bring its effect. Okay, we'll see that in a little bit, but just to illustrate, use an example to illustrate the fact that F equals ma doesn't always, in its original form, give you the most efficient answer to a problem. Let's look at this. Let's look at this problem. Can you try to solve this problem with F equals ma? Okay, what do you mean by this problem? Well, you will see. If I write down this problem, you can see for yourself whether or not it's easy to solve with F equals ma. So we have a situation where we have a smooth track, okay? Smooth track meaning there's no friction. Now, I have a small block of whatever mass, okay? Starting from the initial position right here, okay? I can give it initial speed, or I can just let it slide down from rest. So it slides up and down this track, this smooth track with no friction. Okay, the track is smooth, but otherwise I do not know the shape of this track. Okay, and once I reach the final position, this block reaches the final position, which is the distance h, vertical distance h below the initial position. Okay, so this final position is distance h below, as you can see here, h below. What is the final speed equal to? Well, try to solve this problem with Newton's second law. All I can tell you is good luck. F equals ma, right? So you can analyze the forces. Well, there's mg, but there's also a normal force m, isn't it? Right? There's mg. Everybody knows what mg is. So this is mg. I'm going to draw this. Okay, going downwards. So that is not a problem. I mean, I know what it is. And if the force is only mg, that's a piece of cake. It's just free fall. But there's an addition to that. There's a normal force m, right? This normal force, you know, this red vector, right? This normal force n. And do I know what n is? Well, I do not know the magnitude, do I? Because it varies. Do I know the direction? I don't know that either. The only thing I know for sure about n is what this letter n stands for. It stands for normal, meaning that it is perpendicular to the track or perpendicular to the direction of motion. Okay, that much I know. Okay? So n is perpendicular to b because n is normal to the track while the velocity v is along the track or tangential to the track. So the angle between them is 90 degrees. That's it. Okay, other than that, n is totally variable. Not only is it variable, it varies in a way that you do not know because we're not given the exact shape of the track. Okay, so for example, you can see this at this particular moment, the normal force is like this. Okay, it's like this, but that is only because at this particular moment the track is shaped like this. In the next moment, when the thing say reaches here, the block is here, then the track has a different orientation, and normal force then becomes a totally different direction. It's like this, right? So you see, the normal force turns direction as the course of the track moves around in a smooth curve, smooth and unknown curve. Okay, so if you try to use Newton's second law to solve this problem, you have a problem immediately because we have to start with analysis of force, right? We have to analyze the force, but guess what? You cannot easily analyze the force because there's unknown force here, which is what? The normal force. With a variable magnitude and variable direction, it varies in an unknown manner. With only one thing for sure, that is, it's perpendicular to the velocity. That's it. Okay, so you cannot solve this problem with F equals ma in its original form alone because clearly you do not have enough information about one of the forces, which is the normal force. But you think about it. Do we really want to know everything about this motion from initial to final? Okay, it starts out from this initial state right here. The initial state is right here. And you have the final state over there, right? We're not asked about the actual variation of the normal force. That doesn't matter. We don't care about the normal force at all. We care about the final speed. That's it. Okay, is there a way that can take us from the initial position where the speed is v initial to the final position where the speed is v final? Can we just bypass all the steps in the middle and link initial with final states? So you see, the job is different now. We are trying to link two states. Newton's second law is about one state. Okay, give me the force at this one moment or one state. I'll tell you the acceleration of the particle at the same moment. Okay, so it's a one moment or one state equation. But here we are interested in joining the initial state with the final state. And hopefully we don't have to know everything in the middle. Okay, so it's a different goal that we want to achieve. Newton's second law in its original form needs to be modified to make it better. So we can solve this problem. It turns out that if you rewrite Newton's second law in a clever manner, You can solve problems like that with, it's like a piece of cake. It's very simple. Okay, you can bypass all the detailed knowledge about the normal force N. So you see, problems like that tells us that there is a need to rewrite Newton's second law. So how do we do that? Well, it turns out that is the job for the next 3 chapters, 7, 8, and 9. And let's first look at the roadmap. Okay, what's going to happen in the next 3 chapters now that we know F equals ma? Like I said, everything starts from F equals ma from this point on. There's nothing fundamentally new. Everything is derived from F equals ma. Right here, F equals ma. Okay, but like I said, F equals ma only tells you what happens in one moment. Given me the force, I can tell you how fast the velocity will change. That's the acceleration. It doesn't tell you how much change has already happened to the system. If you want to know how much change has already happened, you don't just tell me the force. You also give me, like I said, give me the opportunity for the force to act on the system, on the object, to bring changes. For example, you can give the system some displacement, and that is, you have this object, right? You have this object. It's being pushed by this force, right? And I allow the force to push on this object, let's say for 3 meters. I want to know what happens at the end of that 3-meter run. Okay, so you give it some space to act, delta R, displacement. Okay, so you're giving the object a displacement under the influence of that force. Okay, this will give you the effect of a force over space, otherwise known as the spatial effect of the force. Okay, you have to combine force and displacement. So the object is being pushed by this force, and as a result, it moves by a displacement delta R. What happens at the end between the initial state and final state? What change has occurred? In doing so, we'll be introducing new methods and new concepts. Clearly, we need new methods to solve problems like you see above, right? And in introducing these new methods, we also have new concepts. And many of these new concepts will go far beyond physics 1A. It goes beyond mechanics. For example, energy. Okay, we first introduced this concept in chapter 7, and energy is a profound and far-reaching concept. It goes far beyond just mechanics. And so the effect of force over space that is studied in chapter 7 and 8. We'll be introducing new concepts such as work and energy, and new methods. You will see that, okay, which will be easily applied to solve problems that you see above, such as the one you see above. Now, in chapter 9, we're going to do something parallel to it, and that is we're going to introduce the effect of force over time. Okay, and that is we give this force, we apply this force on the object, and as a result, the thing has moved, has been under the influence for 3 seconds. Okay, instead of 3 meters. So delta t could be equal to 3 seconds, for example. At the end of the 3-second run, what happened to the system? What did this force bring? Well, in doing so, we'll also be introducing new concepts such as impulse and momentum, and new methods. Okay, this is called a temporal effect, of course, effect of a force over time, temporal effect. So you see, this is what's going to happen in the next 3 chapters. We take that force acting on the object, we give it either some space to act or some time to act. In doing so, we can look at the effect of the force by linking the initial state, that's before the force is applied, and the final state, that is after the force has been applied, over certain distance or over certain time period. Okay, we can link these 2 states. So dealing with 2 states instead of just 1 moment. All right, so that's the basic idea. We're using new methods and new concepts. That's why we have next 3 chapters. And that will, in fact, bring us to the end of our study of particle dynamics. That is the end of chapter 9. So that's the plan for the next 3 chapters. Okay, now let's settle down to study the effect of force over space, and that is we need to combine 2 quantities, force and the displacement of the object delta R under the influence of that force. Right? We need to give this force some displacement to act on the object. Now, the thing is, we immediately have a mathematical problem, and that is we have 2 vectors here. Force is a vector, delta R is also a vector, both vectors. we need to combine these two vectors, right? And how do we do that? Well, some of you may have studied that in your math course, but some may not. We know how to add two vectors of the same type, say two displacements, right? And two velocities. We've done that in chapter 3 and R. But this is something different. We have two vectors f and delta r. They are not of the same type. They do not have the same dimension. We cannot add f and delta r. Cannot do that. Okay. So what do? How do we combine them? Well, if you look at scalars with the same issue, you cannot add two scalars that belong to different dimensions. You cannot add velocity and acceleration. You cannot do that. Okay. You cannot add mass and temperature. You cannot do that because they don't belong to the same category. But what you can do, though, no matter what their dimension is, you get two quantities of totally different dimension, you can still multiply them, right? Multiply them up, right? You can do that. And same thing can happen to two vectors. If they do not have the same dimension, I cannot add them together or take one minus the other, but I can still multiply them together. Question is, how does one define a vector A multiplied by a vector B? That's a new issue that we haven't seen in this course before. Okay, we all know if you have two scalars like 3 times 4, we all know the answer is 12. There's no dispute. Okay, there's only one possible answer, it's 12. Just like two vectors A plus B, right? We all know that have to draw a vector triangle. You can find what A plus B is. Everybody agrees what vector A plus vector B is. There's no second possibility. But when it comes to vector product, okay, vector A and vector B, then we have a problem here because there is not a unique definition of what vector A times vector B should be, right? That is a problem. So you have vector A and vector B. You multiply them together, what do you get? There is not a unique outcome. People can disagree on what the outcome is. In fact, you can come up with your own definition of vector A times vector B. All right? This is not a bad thing, folks. It's not a bad thing because that means, we have the flexibility of defining vector A times vector B according to what we want. And it turns out there are multiple definitions being used widely in physics and engineering. Some definitions are more popular than others. And in this course, we'll be learning two definitions of vector A times vector B. And they will be indicated with different symbols. You see, if it's two scalars A and B, then I know that I can put a symbol like this: AB, A dot B, and A cross B. They're totally the same thing, right? If they're two scalars, right? But if A and B are both vectors, then A dot B, A cross B, and simply AB, with nothing in between them. These three are different definitions of vector products, of product between vectors. This guy, the first one, is called dot product for obvious reasons because there is a dot between them, right? This one, what do we call them? Well, we can cross product, okay? And these are the two being used in this course. The third one is not something we will see in the physics 8 series. It's something that you will find in more advanced math courses. Okay, so we're not going to deal with that. So the first one is called dot product because the symbol we use. It is also known as the so-called scalar product because the outcome is a scalar. You say, wait a minute, you got two vectors multiplied together, you get a scalar? How does that make sense? Well, like I said, you can define vector A times vector B to be whatever you want. I mean, there's no unique definition, so why not? Why don't we can define it as a scalar as long as it's a useful definition that's self-consistent. That's all we care about, okay? And you will find that this, even though the outcome is defined to be a scalar, it is actually very useful. It appears in many combinations, many formulas in physics and engineering. That's where we use it. Similarly, the second one is called cross product because of the symbol we use. It's otherwise known as a vector product. Why? because the outcome is defined as a vector. We will not see that until chapter 11. Okay, so what's next? In the next lecture, we're going to focus on the so-called dot product or scalar product, because this is the math tool we'll be using for chapter 7 and 8. We'll be using this new method, this new math tool to rewrite Newton's second laws, to combine the two vectors force and displacement delta R so that we can see the effect of a force over space. So again, in the next lecture, let's get this math definition of dot product or scalar product, and we can see how we can use it. And then after that, we'll be ready to rewrite Newton's second law using the dot product, so we can then come up with a solution to problems like this. Okay, problems like this. You can see how easy it will be to solve problems like this. All right, so dot product, the math coming up in the next discussion.